Hello friends, today we are going to discuss the topic of design of slip ring rotor of three-phase induction motor. In this we are going to cover the topic number of rotor conductors, area of rotor conductors, rotor windings, rotor core and rotor teeth of three-phase slip ring induction motor. The rotor of a three-phase slip ring induction motor basically consists of a core, a three-phase winding and three slip rings. Generally, these windings are connected in star. The three common terminals are connected together, whereas the other three terminals are brought out onto the slip rings, and these slip rings are rigidly fixed to the shaft, on which the carbon brushes rest, and those slip rings can be connected to the external resistance or other sources for the controlling and starting purpose of three-phase induction motor. Slip ring induction motor has an advantage that by varying the resistance of the rotor, we can have both excellent starting characteristic as well as the speed control characteristics. So the number of rotor conductors of three-phase slip ring induction motor are calculated by considering that at start the three-phase induction motor is stationary, and so long it is stationary, it is equivalent to a three-phase transformer. So using the MMF of the induction motor, that is the primary EMF or the stator EMF is equal to the rotor EMF, we can consider the transformation ratio. As in case of a transformer, we can use the same equation for the induction motor. That is, the ratio of rotor phase voltage to the stator phase voltage is nothing but the ratio of the rotor turns into the this winding factor divided by the stator turns into the winding factor of the stator. So by using the transformation ratio, we can calculate the number of rotor turns, and from there we can calculate the rotor conductors, because each turn will have two conductor sides. So we know the value of stator EMF, we know the number of turns of the stator, we know the rotor EMF, which we can calculate from the EMF equation. We can easily calculate the value of the rotor conductors from the rotor turns. So once we know the rotor turns, we can calculate the area of the rotor conductors, because we know that stator MMF and rotor MMF will have some ratio which will be common under running condition. So at start, the rotor MMF and stator MMF we have considered to be same as in case of a transformer, but once the motor starts rotating, then the rotor MMF will change due to the change in the rotor current, because rotor current depends upon the frequency of the rotor, and the frequency of the rotor we know changes with respect to the speed. That is, rotor frequency is S times the stator frequency, whereas the slip of the motor. Also, we know that the reactance and hence the impedance of the rotor changes with change in the speed. That is, it is dependent on the slip. So definitely the rotor current will change at full load as compared to the stator current. So we are here assuming that let X be the some percentage of the stator MMF that the rotor MMF will have. Generally, if this value is not given, we take into consideration that the rotor MMF is 85% of the stator MMF. So we know here the number of stator turns, we know the number of stator current, we know the number of rotor turns. We can calculate the value of the rotor current, and from there we can assume the value of current density for calculating the value of area of the rotor conductor. Generally, the value of the current density which we can select, it can be same as that of the stator flux density, or it can be different also. So we can assume the current density of the rotor anywhere from 4 ampere per millimeter square to 7 ampere per millimeter square. So area of rotor conductor can be calculated by assuming the suitable current density. Of course, the current density parameter will depend upon the cooling parameter of the induction motor. Then there is a specific, as has been told, that the rotor windings is nothing but a three-phase winding similar to the stator. So we can use all the windings which we use in stator, but generally rotor windings for mush winding is used for fractional horsepower motor or very small type of motor where the slots are basically semi-enclosed. So what we do is we do the winding outside and then we place those windings into the slots. So basically semi-enclosed type of slots are used. For large type of motor, double layer wave winding is used. Now we know that having a layer in the particular rotor conductors will also give an added advantage, that we can call that motor to be having an characteristic similar to a double cage rotor type of characteristics. So having a double layer wave winding will help in the starting torque as well as the running characteristics. So large motors are usually having a wave type of double layer winding. For motor which are above 1000 horsepower, 4 conductor bars per slot are used. So 2 conductors on the upper side and 2 conductors on the lower sides are used for the rotor windings. The rotor core is having dimensions which can be calculated by, we know the stator bore diameter, that is D. If you subtract twice the length of the air gap, we get the diameter of the rotor. This is a very important formula. Usually students make mistakes while using this formula. There is a 2 length of air gap in the diameter. If we consider to be radius, then there will be only 1 air gap, but here we are considering the diameter, so there will be 2 length of air gap. Hence the area of the rotor will be nothing but flux in the rotor upon flux density. We are using the formula for the flux density, which is nothing but flux per unit area. So once we know the flux as well as the flux density, then the area of the rotor can be calculated. Flux density basically is taken as the maximum flux density of the rotor core material. So whatever core material which we are going to select, that will give us the maximum value of the flux density, and we already know, since we know the MMF, we can easily calculate the flux in the rotor core. So based on that, we can calculate the area of the rotor. The depth of the rotor core is basically calculated by using a formula, that is flux upon 2 BCR into Li. So we are using the depth of the rotor core using the formula of flux upon flux density, that is nothing but area divided by the length. We were getting the depth. The inner diameter of the rotor core will be given by the formula, that is Di is the outer diameter of the rotor core minus 2 the depth of the stator rotor slot and the depth of the rotor core. So here we can calculate the total dimensions of the rotor core. The dimensions of the rotor teeth basically is having a constraint that the maximum value of flux density should not be greater than 1.7 Weber per meter square. Generally, the teeth which are, or the slots which we use in case of 3-phase induction motor are tapered. So it is observed that at the teeth, the width is very small of the stator rotor core. So over there the flux density will be very high. So wherever the thickness of the tooth is small, the flux density will be very high, and if it goes beyond 1.7, then definitely it will lead to saturation, and the saturation will lead to higher value of magnetizing current, which will lead to high value of starting current. So definitely, in order to reduce that, we have to have a minimum width of the rotor tooth, which is defined by the flux density to be 1.7. So we are using here the minimum value of the width to be this much. So the constraining factor is the flux density. So the minimum width of the rotor slot is therefore given by rotor slot pitch at the root minus the rotor slot width, and which can be calculated by using this mathematical formula, where this is the rotor slot pitch and this is the rotor slot width, WSR. Thank you friends. If you like this video, kindly do comment, like and share. Thank you.